try to start talking about more quantitative aspects of calculating the kind of things I was talking about. So, as we sort of discussed, there's this. I have a family of diffeomorphisms of this manifold. Obviously, one, you can look at what that diffeomorphism does at the intersection. This gives you a homeomorphism to either the symplectic group, if n odd, or the indefinite order. And I was, as I said, sort of introducing framings to everything turns out to be an advantage. So you can also recompose that to the map that gets So there's two bits of notation I want to introduce here. So one is that the kernel of the composition corresponds to some covering space of beta framed, and I'm going to call that the framed Torelli space. Responds to the B Torelli.
Can you just remind, if somebody was here or forget, or for Mole who forgets, what WG1 is?
So it's a genus G surface with one boundary, except for the dimension to it. It's the two edges connect some with G copies of extends 9%. So its intersection form is a hyperbolic form, okay? Either symmetric or skew symmetric, depending on this case. So the kernel corresponds to some covering space that I'll call the Torelli space, by analogy with what happens in the case of surfaces. And the image is some finite index group, which we actually know, but what it is not so relevant. The image is finite index group. I'll call it GG. So it's finite index of these. In fact, in this case, it's the whole group, but in this case, it's the subgroup that stabilizes it quadratic. I want to say two more qualitative things you can prove by doing exactly the same strategy as I explained last time, by using this white spider sequence and then going up the embedding tower. Strategy is the same. There's plenty of complications to do with spaces not being connected or pi ones being not quite what I'm saying they are, and so on. But two things are true. One is that this space, this framed Torelli space, is a nilpotent space in the sense of homotopy theory. Its fundamental group is a nilpotent group, and it acts unipotently on all the higher. So that was, of course, completely not true before we took this cover, because it contained this great big arithmetic group. Something like it. And this, you can imagine, I mean, nilpotent is basically the best possible example of a property that's really good to check by checking it on subquotients and extensions. If you have spectral sequences converging to something, you can check nilpotence with the E2 page. Somehow, it's almost adapted to kind of argument that I explained. And the second property, also sort of qualitative, is that cohomology, say with rational coefficients, because it arises as a regular cover of B diff associated to the group GG, it comes with an action of GG. So all the cohomology groups are representations of this arithmetic group GG. And we know they're finite dimensional because we proved that these were finite last time. But in fact, they're much better than just finite dimensional representations of GG. They're so-called algebraic representations.
Sorry, and you're assuming here still that 2n is greater than or equal to 6?
Yes. Yes. Otherwise.
Right.
Yes. So these are algebraic.
Although it's false.
And I'm also
real two real dimensions. It's not true that H star of B Torelli is finite dimension.
No, it's not true. Right. So yeah, so all the conventions from last time so Qn is B6, and also for some of these algebraic group things, I'm going to say it's convenient to say that group is semi-simple. So let's say G is at least 2. So they're algebraic representations. So what that means is, if you like, the following: if I complexify this and think about it with complex coefficients, then the action of this integer points in SP2GZ extends to a holomorphic representation of SP2. And the point is that algebraic representations of either of these algebraic groups, we just know what they are. You know, the category of them is semi-simple, so all you get is direct sums of simple modules, and they're described by sort of Young tableau. So in particular, we have names for them. And at this point, it then becomes a legal question to say, what is it? Which, for example, before we knew it was finite dimensional, that was not really a very sensible question to ask. But once you know it's a finite dimensional, irreducible algebraic algebraic representation, you can try to ask what it is.
By the way, I'm curious, to prove it's an algebraic representation, you use either Borel density, or do you use superrigidity, or?
Yeah, we use all this.
Okay.
Yes. Yes. I mean, being finite dimensional is not quite enough to be an algebraic representation, but it's almost.
Or something like SP2GZ, it's enough to prove your image is infinite.
Yeah. So yeah, we do lots of tricks like that, but I mean, all somehow well-known tricks. Okay, so that actually is the end of the last measure. That's the qualitative aspect. So, so quantitatively, you can now try to ask, so what is it? So I want to try to tell you what the answer is for what is the cohomology of B2L in a stable range. And that requires explaining something about so-called minimum multiple classes. Sort of not the classical ones, but certain twisted ones. So this B2L frame, WG1, classifies a certain kind of data, and the data is a WG1 by one over some base, a framing of relative tangent bundle, some boundary condition stuff which is somehow tedious. And so far, this would be what B-diff frame classifies. And the difference between that and B2L frame is the additional datum is it's equipped with a trivialization of the local system given by the middle cohomology. So I'm going to use this somehow script letter H N to mean a local system. In fact, it's the integers. And these come trivialized. So it's identified with the constant local system by and that's what the data of the two-ediness does. And the action of GG on this space is by re-trivializing it, by composing with an automorphism. That's how GG acts. So imagine we have this kind of data. The boundary conditions mean that, in particular, we have a section by picking one point of the boundary is fixed. Like that. So I want to think about what the Serre spectral sequence tells me about nth cohomology in this situation. So it says that fiber has relatively sparse cohomology. We get from the Serre spectral sequence in degree n is shortly that sequence like that, and it's exact because the section keeps the splitting. So there's no possible difference. Well, this spectral sequence only has 2 rows, and there's no possible difference. Now, a splitting, or this kind of splitting, induces this kind of splitting. It's quite algebra. So we get a canonical map iota from this fixed vector space into the cohomology of and then you can form the following thing. So this gives a map out in kappa. It goes from maybe the rth tensor power of the middle cohomology of the manifold And it's going to go to the cohomology of the base in a certain degree that I will work out in a minute. And it's given by the following rule. I take a tensor, B1 up to BR. I use this map iota to think of these elements as being cohomology classes on the total space. And then I cut them all together. So that's the cohomology class on E. And then I fiber integrate it from E to the base. And that gives me a class of degree Rn minus 2. And this is some invariant. And you can do this whatever the family is, in particular, you can do it to the universal family. So these are defined universally in the cohomology of the some so let me state the theorem of what the cohomology of these really looks like. It's yeah, there's a small issue. You need to promote them to the base, which you can do. Let's just follow it. So there is a fiber sequence vibration. It turns out that what we describe won't really directly be the cohomology of B20 frame, but it will be two pieces. Two spaces called x0 and x1 of G. So x1 of G depends on G and x0 is not G. With the cohomology of x0 is quite easy. It's depends on these two cases, but it's an exterior algebra in both cases, and it's an exterior algebra on classes and degrees 1, 5, 9 in the first case, and probably 3, 7 in the second case. So this is n odd even. That's just a simple thing. In fact, x0 is even an infinite space. It's a very easy structure. And x1 is generated in a stable range. So a stable range always means some range that I don't want to tell you that goes from infinity to G, and we can work out if we wanted to. In a stable range, by these classes. Are at least 3. And if I was too small, like this is a negative, so start with 3. Subject to, so those are the generators, and then there's a complete list of them. I mute the entries. I pay a price, which is a sign with a permutation to the power n. So sometimes it's there, sometimes it's not there. What I do if I don't mute them. That you can prove yourself. The interesting one is the following. To introduce a notation, let me write AI hash to be the element in the square. This works into this vector space, which is dual to the intersection. It's the thing that's dual to itself under the isomorphism given place. It doesn't depend on the data. So in other words, I'm saying that AI be a basis of this, and that AI star be the function basis. So then there's a relation that goes as follows. Sum over I of kappa V1 up to Vi minus 1, no, AI, kappa AI hash Vj plus 1 up to VR is kappa V1 V. And I already forgot to do the most important psychological thing here. It's very advantageous for turning formulas into pictures to think of this class as a corolla, meaning a graph with one vertex and some legs, where the vertex is whatever it is, and the legs are labeled. And it's very advantageous to think of this element as an edge. And therefore, it's very advantageous to think of this formula as saying two corollas with the edge between them is the same as the thing you get by collapsing it. And this is not just a heuristic, because thinking about things in this way these weeks. So there's a few more. One more thing, I suppose. Which is somehow, so this is telling you what happens if you take two corollas and you pair one leg of one with one leg of the other. But what if you take one corolla and pair one leg of it with another of itself? Like that, and the answer is you go. So graphically, this is saying this is the same as the.
So this feels like a Steinberg module.
Ah.
We do modular symbols to get some of the same.
Uh-huh.
Yeah.
Right. So and that's the confusing. Maybe I didn't know if I said it, but it's sort of by definition it's linear in all the things to be honest. And that's a complete presentation in a stable. Now, it's not an efficient presentation. I mean, it's not supposed to be. It's to be a natural presentation given these naturalistic generators. But using this relation in reverse, you can clearly take any kind of graph picture and use this backwards until it's trivalent. And that just actually implies that, in fact, kappa V1, V2, V3 generators. Take any corolla you have and keep using this relation backwards towards the denominator of the trivalent. And then, if you've got a presentation and you've got some elements that you know generate, then you can just try to work out what the relations among those elements are that present the same thing. You discover that among these, the relations are quadratic, meaning they involve pairs of products of the two of these elements, and correspond to you see, if you're allowed to have a four-valent vertex, these are obviously because they're both equal to the letter x. I can track this edge, I can track that edge. But you need to write down relations that make sense among things that are only trivalent. This is the best thing you can write down among trivalent graphs, but when you allow all valencies, that's a complete simple presentation. And another thing I should have said, of course, I should have emphasized that the reason for writing it in these terms is that the way GG acts is by acting on the symbols VI. This domain is the standard representation. So this is a description as a ring, but also as everything. Let me just state here. So I want to say something about justifying why it's more feasible to do this. And let me state a follow-up theorem. Everything is this. If you have an algebra with only quadratic relations, you are forced to say, I wonder if it's causal. And it is causal. It makes sense to be causal only up to a certain. And if I have a space such as x1g, which is nilpotent, in the sense of rational Hamilton, I said that that's where the space was, but x1g is similar pieces. And you know the cohomology, then you can try to calculate the homotopy groups using the Adams spectrum, the unstable Adams spectrum sequence. And in general, that's the spectral sequence, and things will happen. But if the algebra is causal, that spectral sequence must immediately do it. And the homotopy groups must be the causal to the algebra. So the immediate conclusion is that the homotopy groups of x1g rationally are the causal to which is, let me just write down the form it's so it's the Lie algebra on the representation given by three such things, satisfying two relations, which is the symmetry relation, and the fact that if you insert the symplectic form, you get 0. What that turns out to be is either the representation called B1 cubed or B3, depending on the case. And then you divide out by certain relations inside B2. We know what they are. They correspond to this I equals H thing. You have to expand it out and do some classical representation. It's completely explicit. And this, of course, is including I think exactly three things. I landed with it.
Was that first one like what the third exterior power?
Yep.
This guy.
It's the reduced one. It's the 33 pound.
Yeah, modular,
It's the reduced. So, an immediate consequence is that all the homotopy groups, we shift them by 1, are in degrees and multiples of n minus 1. This is an incredibly sharp, I hope you agree, pattern of bands that have 0 width in.
This equality is also
In a way, everything is yes. In fact, this is brutally, it's not actually. So let me just say an aside for something that you may be interested in. From the point of view of pure algebra, this situation is very similar to the classical 2A. And you can make it algebraically identical to the classical 2A group, not by using framings, but by using the tangential structure that keeps the order class and kills all the contrarian classes. That's exactly what happens with surfaces. They don't need an order class. And if you do that, you can run a similar rigmarole and you discover that you get a certain algebra. This is an algebra that was written down by Getzler and Felix in the 90s and then released about 20 years later. They conjecture that that algebra is causal, and that algebra is this algebra, and it is causal. And in that case, its quadratic dual is Haynes' is an algebra completion of the classical 2A, the algebra, and so that proves that that is the causal algebra in stable. But the strategy is kind of incredible. You just use that algebraically, surfaces are indistinguishable from high dimensional structure. And then you use high dimensional topology tools that are not available for surfaces. You don't care because the let me try to say something about why it's plausible to calculate this kind of thing as well. It relies on knowing a priori that they're algebraic. Of course, if you believe that claims they are algebraic a posteriori, because I'm saying they're isomorphic to these specific algebraic. But you need to know that they are algebraic at all for the strategy to work. And the idea is as follows. You think about the Serre spectral sequence for this, the defining covering space of the group, with coefficients in tensor powers of this fundamental representation. So that goes from homology of PG with coefficients in maybe to any space, tensor, maybe some tensor power of the fundamental representation, and it converges to the cohomology of B diff, framed with twisted coefficients in this way. Now, I think overall, if you know this is an algebraic representation, you can calculate the cohomology in a big range of a large rank arithmetic group. And what Borel tells you that this, in a big range, is the cohomology of the infinite version of the GP times the invariance of these coefficients. Another way of saying it is that every non-trivial irreducible representation simply does not contribute. Now, if I have a representation which I know to be an algebraic representation, namely cohomology B to A, if I know all of these vector spaces, that's quite close to knowing what the representation is. You need a bit more data, namely you need to know the maps induced by pairing pairs of these agents. But if you know that data, then that recovers that Shobart duality in a sort of. So if you knew all of these functorially in its power, essentially, then you would know the
Or you mean all of them when S varies?
as S variance, yes, as a function of our count. So it's massive sections. So what you can try to do is calculate the twisted cohomology, try to argue that this degenerates, and say that you would want. It turns out in the frame case, it doesn't quite degenerate, and it's something more complicated. If we didn't do framings, this in fact just works exactly like this. So you have to do something a little of that nature. So that reduces it to computing twisted cohomology would be different. With these tensor power coefficients. So you have to come up with some strategy to do that. So the first strategy I know to do something like that is due to Euler-Jenke in the case of classical modular spaces of Riemann surfaces, where you try to calculate the cohomology of energy with coefficients in tensor power to the hot bundle. What he does is take fiber powers of the universal curve and rely on Deline's degeneration theorem to say that the sequence degenerates and calculate what the total space was and deduce what was happening in the works. So with manifolds, you don't have Hodge-Debye available, so you can't do that. But essentially, there's a different strategy. You can think of taking fiber powers of the universal family as taking spaces of zero cycles, the universal fiber. And instead of using zero cycles, you can somehow do spaces of cocycles. It's a much more algebraic topology way of doing things. And if you do that, you can run a similar kind of game where you can calculate these from knowing somehow the untwisted ones and enough functoriality for various directions.
How in the end do you get a hold of the cohomology of the total space? You
That's
can't
right.
use
So let me give you a better. So exactly. So that's not what we actually do. What we do is the following thing: that all these Mass and Weierstrass theorems come with many bells and whistles and tangential structures and so on. So we've already used framings. But another tangential structure is you can just fix a space and take a continuous map to that space. So I can look at maps from WG1 to some y times the space of framings mod diff or out diagonal. And there's a massive Weierstrass theorem for that. And the target, the way it changes, is you get x minus 2n, as we got before, smashed with space. And this will be a homogeneous isomorphism in the way. And the excellent trick is to just consider y as a variable. Both sides are functors of y. And in particular, if their homologies are the same, then there's different ways to do it. You could take Goodwoody derivatives in the y variable and say that the coefficients have to be the same. Or you could do something more manual involving taking homology. The strategy, basically, what we do is we take y to be an unbound plane space for a vector space W. And then use the action of scalar automorphisms of that vector space W to argue that the sequences generate because they act differently. It generates and you can identify weight spaces here with the corresponding weight space. So this is sort of what I mean by taking fiber y. So when y is an unbound plane space, that's like taking the space of the cocycles. So that's how the analogy with the method that I learned. So this is by now a somehow standard method. This has been used. So I actually started to use this method to study Alt Fn with coefficients by thinking about modular spaces of graphs with a map to y. But people have used it more recently to study weight groups with coefficients in a VOL representation, things like that. So that's somehow why this is important. Okay. So maybe that's all I will say about the D2N term. I could say something about the embeddings term. So now we need to actually quantitatively deal with all this embedding calculus story, at least estimates about what kinds of degrees classes lie, and maybe not completely calculate what they are. So the layers, to remind you what they were these section spaces with boundary conditions over the space of unordered configurations of K points WG1, whose fiber was this fiber over one side, something. And that something was the total homotopy fiber of the cube that to a subset of psi takes the embeddings of S into also WG1. Somehow this is the domain WG1 and this is the type WG1 because we're studying self. So how can we try to calculate anything about this? Well, there's a spectrum sequence computing homotopy groups of mapping spaces and section spaces to go through just as well. Better a spectrum sequence. And it will go from the cohomology of, in this case, the unordered configurations, K points, relative to where we've imposed boundary conditions, some sort of open neighborhood around the diagonal and near the boundary. And then it will take coefficients in the homotopy groups of the fibers. The embeddings of a finite set into WG1 is a configuration space. And it will try and maybe succeed to go to pi q minus p. And there's all sorts of things we have about base points and conditions and so on. Here, typically, this will also be local coefficients that depend. I mean, somehow you have to encode which vibration you were talking about. It's encoded to zeroth order in the what the so we only want to calculate rationally. So let me implicitly rationalize everything. I don't want to write it down. And then it's a little unfortunate that we're doing unordered configuration spaces here, but I can, because I'm working rationally, or I allow myself to work rationally, I can change that to doing ordered configuration spaces, and then taking symmetric equivalent. And in fact, when you do that, this space now becomes something so it's so that's the kind of thing that you need to get. And we do some complete calculations. In fact, we give a complete formula for all these rational homotopy groups. But for what I'm trying to explain, we just want some estimates, so let me not try to be too precise. We just have to look at where these two kinds of terms, the cohomology configurations or the homotopy fiber, can have something going on. So using some excision, configurations relative to a neighborhood of the things I cut out is exactly the same as Cartesian power relative to the fat diagonal, which I'll still call that. So right, that's a kind of simplification. So how can we control a little bit where this pair has homology and where this total homotopy fiber has homotopy? Well, WG1 itself is a web of n spheres. So it's K Cartesian power only has stuff in multiples that are multiples of n. And that's exactly the kind of pattern we're trying to show. What we want to show these homotopy loops are supported near, where near is allowed to depend on k. Maybe it means plus or minus k degrees, roughly, multiples of n. And WG1 already has that property. What about the fat diagonal? Say WG1 to the k has cohomology at multiples of n. The fat diagonal you can stratify by the thin diagonals, and the thin diagonals are all Cartesian powers, so they all have stuff in multiples of n. And then you have to run a little spectral sequence for that stratification. But that stratification has approximately k layers. So that spectral sequence will have about k rows, each of which is supported in multiples of n, and that gives you a little offset of plus or minus k degrees. So this is stratified by the L's with sort of a depth at k, and then the kind of Livertorius spectral sequence for that cover will tell you that it has homology in lambda times n ranges like that. Okay, what about this total homotopy fiber? So as you can see, you can be rather robust with the stage of the game. For the total homotopy fiber, I want to do a similar thing. It's a total homotopy fiber of a k-dimensional cube. So as a bad estimate, I can just take the homotopy of all the entries in the cube, and then there will be a height k spectral sequence. So I can just study ordered configurations like G1. And if you just want to know homotopy groups and you don't care about naturality, and this is very easy to study because they were just mapped to the forgetting point. S. Forget little s, and the fiber will be all ways of putting that point little s in that does not hit the ones that you already had. Namely, it will be WG1 minus s minus. So in other words, it's WG1 minus some finite. If you remove a point from an open manifold, you wedge on to a minus 1. Again, just by fairly coarse estimates in rational homotopy theory, this will have homotopy groups that support it near order. They become less near as you move up, but that's allowed in this. So this has deductively, of course, you've dealt with fewer numbers of points already.
That's for 2n, we're in 2n now.
Yes.
Yeah.
So you wait on, yeah. That's the next right, so, okay. So you can, and then of course you get a certain error term because you're taking one pet to the other, so maybe that error's add a little bit, but I mean, up to some finite amount of noise, we get this. And if you're a little careful with that, so exactly this idea with the application of care, you get that homotopy of the Pirelli version of the embedding space, meaning the corresponding color, named one and recognized, is supported in the following range. R times n minus 2, so R times n minus 1. So it's, in fact, it's actually most naturally said that it's supported in multiples of n minus 1. But this is the conclusion of this rather coarse estimate. Like I say, what we actually do is we give a complete calculation of all the homotopy groups of all the layers as GG representations and as symmetric representations. Except that we don't know how the layers in a tower assemble. So it's very difficult to know, even though we're sort of a bit heroic to do this calculation. But we could have got away for the sort of results that are formulated now. As I said here as well, of course, the homotopy of this x1g is supported in multiples of n minus 1 plus. So let me draw the fundamental diagram of this business. So there's the framed version of this Y fiber sequence, and let me go to the corresponding covering spaces that correspond to the 2 group. This is 2 version of so embeddings, so half the boundary. And then there's the vibration up in the top of the middle of this board, which describes B of the 2 in terms of these spaces x0 and x1g. Okay. And x0, I wrote down the cohomology completely. It was a free gradient commutative algebra on some elements. So its rational homotopy is just a free vector space. Degrees, 4 degrees, starting at 1 or 3. And x1g is what this theorem is about. B2 embeddings is what this thing is about. Now, if you have a diagram of this shape, it is a amusing exercise to convince yourself that the homotopy fibers of those maps are equivalent to them. But this, and what we know, starts to have very striking consequences. I want to spell out. And this is where all the story can't finish. Because if we think about F as the fiber of the top map, then all these spaces have homotopy groups that are supported in multiples of n. Or supported in this range, let's say. This one's supported in this range, this one's supported in a much tighter range, which made us great. And so the homotopy groups of F are supported in that range as well. And there's some representations of the group G. If we think about F as being the fiber of the bottom map, then there's no action of G. It's trivially here because this is just a little neighboring the boundary that needs to be morphed to actually. And this, by definition, is a space. So we deduce, that the homotopy groups of F must actually be trivial. Think about it from the bottom. And it must be supported in these certain bounds when you think about it from the top. And the fact that it must be trivial representations is, on the face of it, incredibly surprising. Because that says that all the non-trivial representations in these, of which there are many, must cancel out. And only trivial representations contribute to that. And if you go ahead and calculate the homotopy of this by the formula I gave, and you go ahead and calculate the homotopy of this by the formula I gave, you see that there is indeed some incredibly complicated pattern of differentials in the embedding calculus cell that makes almost everything apart from the ones that you know are supposed to be there. So firstly, that's an excellent sanity check for the entire program, because calculational things, of course, AI is very unfair as a calculator. So somehow it's quite good to have a check that is somehow irrefutable. But let me just write down then the takeaways. So homotopy of x1g and homotopy of b relative embeddings. I suppose it in that way you work up there. In fact, yeah, let me just So on top of F, maybe with one little loss from a connecting map or something. And secondly, so homotopy of E diff a disk, and homotopy of X0, which is incidentally just vector space sigma 1. Space of sigma 3, sigma 7. Are trivial G representations of the homotopy of history. And there's one more thing I want to point out. Nobody called me out on why the answer takes this strange form with x0 and x1. It's a little bit unpleasant. It would have been nicer in some sense if this formula here was just a cohomology of B2A. I mean, you'll notice that all these classes kappa are defined already on B2A. Like where defined was B2A. This x0 comes from the following. It's a collection of secondary characteristic classes associated to the so-called family signature. So the signature theorem on a manifold says you can calculate the signature of the manifold, meaning the rank, positive and negative eigenspaces of the intersection form, by integrating the physical L class of the manifold. There's a family version of the signature theorem which says you can calculate the family signature, which is basically something like a Schoen class of by fiber integrating family objects. And the L class only depends on tangential data. And the first thing only depends on intersection data. Now, if I have a bundle which is simultaneously framed and Torelli, well, the framedness kills the L classes. So it forces the family signature to be 0. But the Torelliness also kills the L classes because it trivializes the family intersection. And those reasons are probably not the same. And they're actually not the same because these classes sigma I are exactly the secondary classes. By transcript. So this doesn't happen if you don't put framing. You get a in some sense a simpler answer, but but I say that to explain that x0 has something to do with signatures, and in fact, you can identify x0 framed. Argued by this Morley principle last time was root to n of top line. And this x0 you can identify with root to n of 2. That's the space that signature type things live on. And so from that point of view, so that's only last identification. But from that point of view, this fiber is root to n of top. So that's the thing that has these two striking properties. It obviously only contributes to trivial representation because there's no action, there's no WG inside. But also it's homotopy supported. And that's how it explains the picture on my slides on the first day, that there's an underlying pattern, which here I've hidden because I've taken the difference. The underlying pattern is the homotopy at the top. And then the truth differs from that pattern by something that's supported in this sequence of patterns, various widths. Right, so that somehow is my justification for for this chart I showed you of my standard groupers. If you go very carefully through what I've told you, you discover that the chart's a little bit better than what I've told you. That's because, for example, we completely calculate what happens in the first band. We see that the contribution from this Torelli exactly cancels out the contribution from the embeddings, and so you don't see a first band. So there's a few bells and whistles on that I explain, but they're all in the spirit. Maybe we can stop here and have some extended.
Question? Graph cohomology.
Where does it show up?
Yeah.
I mean,
Right there.
so
So yes, that's the beginning.
But beware. This is it looks, of course, superficially very similar, but it cannot be actually very similar because I'm saying these classes are equal. In the graph complex, there's a differential given by contracting agents, and these classes are not even in the same degree. So these pictures are necessarily somewhat different to the pictures the graph complex in fact, it comes from what we're going to see is that there's a graph complex of graphs with edges of two colors. I call them red and black graphs. And the differential is given by summing over contracting black edges. And these are somehow red edges in that picture. So red edges have degree 0 in some sense, and black edges have degree -1. And there's another proof, in fact, of causal duality in this algebra due to Felder, Neff, and Wilwacher, where they just work with the graph complexes and manipulate them and so on. They don't invoke anything about the manifolds. So I like our argument, but there's a pure algebra where these red and black graphs show up. So that's somehow one place where they show up, namely here, or somehow corresponding to this term. There's something to do with this, or rather this term, in fact. There's some kind of graph complex of red and black graphs, and it's that's much simpler than the ordinary graph complex. I've given you a formula for its presentation for this quadratic algebra. There was no differential. That's a formula for its code. So this complex of red and black graphs is somehow much simpler than the complex of just black graphs. But it contains, of course, the complex of just black graphs. And that somehow is this map. And what one has to do to prove something like this conjecture that I was proposing, one has to show that the difference between those graph complexes is modelless. And certainly this is modelled by some kind of graph complexes, because graph complexes show up as models for, it's like minimal models in the sense of Sullivan, but for models. And embedding calculus can be rephrased in terms of maps and left models. Somehow there's some kind of graph complex there, but then there's many subtleties about what does model mean and like this. But myself and Sander Coopers and Thomas Wolbach were trying to make that work out. And so that's somehow, at a conceptual level, it's completely clear. But there's difficulties to do. But that would be in some sense you would avoid computing anything about this space. You would just show that this space models this, like the cone of this graph complex. And this one you've computed. And so this one models the thing divided out by. And you wouldn't actually ever compute this third term. You'd use conversions, embedding calculus, to say that it's the same as some other thing that you also not going to. So that's somehow going to be the strategy. But I have been saying this for some years.
Is it? Okay. I was going to say, stepping back, you're telling us about at least rational homotypic groups of diff of them all.
Mm-hmm.
For pi naught, that converts, that was Milner's point of view, gives you exotic smooth structures with spheres. Is there a conversion of these things to give you other kind of exotic? Because it seems like you've also discovered many classes.
So, I mean, one way, yes, maybe I can say the following. So, I mentioned this Morley theorem. But that's actually not just for this, it's for any manifold, and it's maybe better called the fundamental theorem of smoothing theory. And what it says is that for any manifold, maybe pick a smooth structure once and for all in your mind. You look at homeo and model of it. Then this is equivalent to a space of sections over M, would be M d-dimensional, whose fiber is d modular. It's twisted in a way that's controlled by the tangent. Maybe there's boundary. But if you mean exoticness, as in the difference between topological and smooth manifolds, then this is exactly the entire difference between M viewed as a topological manifold and M viewed as a smooth manifold. This is the space. Speaking of some, this is the space of smooth structures on the topological manifold. It classifies smooth bundles with a topological trivialization. In other words, it classifies smooth structures on the trivial bundle. And it is just sections. So oops, the property model. I mean, okay.
So in theory, you can calculate.
I mean, we've
Think about, like,
computed homotopy of this up to some big range, like 2.5 times d. That's what these charts are about. I guess I wrote them without the OD, but that makes it very mild. So by pure homotopy theory, yes, you can just take maps from M to that or sections or something, and that will give you loads of stuff in your spaces. But it's somehow.
So can you plug in? Sorry. So for any manifold,
Yeah.
you can sort of figure out space is smooth. I mean, can you? Right. Okay.
So I think it. So if by exoticness you mean the difference between smooth and topological, I think this is somehow the complete story. And understanding about that
condition when you can get like finitely many, and this is the finite. Or sorry, I think of finite.
Yeah, okay, but I mean,
no, the number of smooth structures. Yeah, I want to know when you're finite.
Yeah, I mean, you can for sure. So I guess for that you don't need all of this, because if you just want to know pi zero, so this is a d-dimensional manifold. So sections basically needs maps from that. So it's a d-dimensional manifold. You only need to know the d type of the fiber if you just want to know pi zero, and for that you can replace it by topology.
So pi zero will tell you about like exotic smooth structures on the. You know, when you have things are homeomorphic but not diffeomorphic. That's like
so right.
So what is these higher things? Is there like
so that right? So you don't see the higher things if you just look at pi zero. You need to talk about families, yes. But in some sense, I mean, just like smoothing theory, it says that what you see is what you see in the disk, somehow smeared out over the manifold.
Right.
That's what you're going to see. Yeah, so certainly you're going to get some high non-trivial rational homotopy groups, but I don't think it's so any new. It's just somehow a translation of the phenomenon of disks, and then the fact that you can build manifolds like blue disk.
I guess Benson would like to see some beautiful examples of smooth bundles that are topologically true, or something like that. I think that's what he's really designed.
You're going to use this. If you come up with all these, one of the super specializing your thing, you come up with new classes.
Yeah,
they can detect
something. Yes,
things.
Yes. But I mean, so the conjecture says that, in some sense, from that point of view, the conjecture is disappointing in that it says that there are no new invariants. They're exotic programming classes that Michael Weiss found, and then there's these configuration space integral classes. And what the conjecture is saying is that those configuration space integral classes are actually not trivial, which is not known.
But I thought also you're getting secondary classes. Characteristic, kind of secondary.
Yeah, okay, but that somehow is the artifact of putting the framing. When you go back to naked manifolds, those go away.
But I guess you could, you could write down bundle of topological manifold that needs a smooth structure fiber-wise, but you can't write down.
Yeah.
Right, that would be
Yes, I agree.
Yeah.
But even Benson could do that as a homework problem over a circle. So that can't be what there.
I was. No, I could do that. Yeah, exactly.
So you said the Zuulness is proved topologically instead of algebraically?
That's how we do it. I mean, so there's also this other paper that was an with about the same time. But our strategy is, I mean, I can sort of say here, if I don't use causalness, you can also try to use the Adam spectrum sequence to compute the homotopy of X1G, knowing the cohomorphism. And the cohomorphy supported degrees in the multiple of n, and the Adam spectrum sequence in sort of ordinary indexes will be supported on some lines like that. which that's like multiples of n, and they have certain width, but they sort of don't overlap. And what you want to show is that it's somehow actually supported. But if you look at where these bands are, they turn out to be not very similar to these bands. Namely, they somehow go from that point downwards instead of from that point upwards. And what that tells you is that because the difference is trivial representations only, that it has to be somehow causal, except for maybe trivial representations of the day. And that comes from this geometric argument. And then you have to do something to also account for it, which that is a more just a graph complex plane. But it's somehow quite important that the algebra is the same independent of the dimension. I mean, okay, there's a parity condition, but if I replace n by n plus 4, algebraically it's identically the same except for the degrees are split. But so you can somehow use these sequences to study that algebra by picking n to be big compared to whatever specific question you're asking about the ring structure.
Yeah, it's like the same trick again, right? In a meta way, that's what you're doing for studying something. But you're taking very big instead of taking small.
Yeah, right, but it's somehow in the n direction instead of g.
Yes.
But I mean, I'm pleased with our proof of causalness, of course, but obviously the purely algebraic one is somehow correct.
Thank you.
Thank you.